Alright, so welcome to the final part of homework 1, where in this part we're going to be exploring a situation where we have, let's say, a beaker full of some liquid, right? And let's put this beaker on some kind of rotating plate, okay? And you will know from experience that if you spin the plate slash beaker around, the liquid is going to start to concave out, right? It's going to start trying to fling itself out. So the question is, how fast can I spin this beaker? How fast can I spin this beaker until before the liquid starts flying out all over the place? So let's start doing that. And our starting point is going to be the basic equation of fluid statics, which states that the pressure is dependent upon some change in altitude, right? Now that's altitude. I shouldn't say altitude. Some change in the position of some axis. Okay, that's because in this case we have acceleration in two axes. Okay, and that's equal to the density multiplied by the acceleration. Okay, and normally you see this as rho g. And you see we do have acceleration downwards, but we also have acceleration, circular motion, right? And you will know from physics 1 that whenever there's circular motion, well, there's acceleration inwards. No, but from the fluid's perspective, it's actually centripetal acceleration. It should be outwards, that imaginary acceleration force that actually doesn't exist, right? So we're going to say that, and you'll also know that from your physics formula sheet that, centripetal acceleration in terms of angular velocity is equal to what? R omega squared, right? But let's go take a second and derive that really quick. Where does it come from? Say you forgot it. How do you find it? Well, if I can get a circle. There we go. Okay? Well, so let's say I want to describe the position of a point on a circle in rectangular coordinates in terms of theta, right? And you'll know from your calculus 1 class that, well, x is what? R cosine theta, and y is r sine theta. Theta is what? Theta is displacement, right? And in rectangular coordinates, or Cartesian coordinates, you'll know that displacement is equal to velocity times time. Now what about theta? What about polar coordinates? Well, you'll know that it's supposed to be time times omega, right? Or actually, maybe I like omega time better. Omega times time, right? So theta, you can replace theta, you can replace theta with omega time. What else do you know from calculus? Well, if this is position, this is s of t. If I derive it once, that's v of t. And if I derive it twice, that's a of t, right? So we're pulling out all the tricks here. So if I want to if you've taken ODE before, you've probably learned this trick. And if you have some trig function, in ODE, you'll find that you have to double derive, sometimes triple derive quite a lot. And you'll learn shortcuts to make your life a little easier. And this is one of those shortcuts. So if you want to take something away from this video, maybe take this away. If you want to double derive this, so dx with respect to time, all this is the negative of what's chain rule, right? If I'm deriving with respect to t, that omega is got to come out. And if I'm double deriving, well, it's got to come out twice. So r omega squared, and then just square the trig. Okay, so I don't have to waste too much time doing product rule. That's all it is. Same deal here, right? If I take the second derivative of the y coordinate with respect to time, second derivative, it's negative r, pull out the omega twice, times whatever the trig is, right? Now, this is the components of my acceleration vector. If I take the magnitude of that, I'm gonna do what? That's the magnitude equation, right? Now, I'm not gonna waste my time with algebra because I want to get on with the rest of the derivation. If you plug that in, you'll find that that is going to be your centripetal acceleration. Okay? Now let's get on with this and see what we can do here. Again, we'll take our basic equation of fluid statics. So let's get on with the derivation of finding the maximum velocity that this can spin around. So if we take our basic equation of fluid statics and plug in our angular acceleration, our formula for angular acceleration, it states that, well, it's going to equal to r, we're going to use a little r here, omega squared, right? And what do we have here? We have a separable differential equation. So let's go ahead and separate and sub that. We have dp is equal to rho omega squared r dr. Okay, remember z is not necessarily always altitude. It may be the axis of any particular position. So we call it dr in this place, the radius of the cup. So let's go ahead and wiggle this out. And we always ask ourselves what should be our bounds of integration. And remember, these become dummy variables of integration. And we say that, well, we know the pressure and radius at a particular point, and we're exploring the pressure and radius at another point. So then this becomes what? This becomes P minus P1 is equal to rho omega squared R minus R1. Okay? Here's our first important equation. Let's highlight that. And if we're taking a look at this idea of a spinning cup full of fluid, okay? Let's define this as our initial point. And we're going out to some radius, okay? Some radius, and this some radius actually has some amount of fluid above it, and that contributes to a pressure of what? Rho GH, classic, right? Classic. So let's do that. Well, if I say that my initial pointance right here, then, well, pressure is zero. Gauge pressure, the pressure in the fluid is zero anyway, right? So pressure is just equal to rho omega squared. If I'm right directly to the center, what's the radius? That's not a trick question. It's zero, just zero. So pressure is equal to rho omega squared r, right? Again, at this point, the pressure, this is going to equal that, okay? So now I equate my two equations. Rho GH is equal to rho omega squared r. My rho's cancel out, so I have GH equals. Ooh, I realized something. I failed to integrate. This is the integral of r dr. I made a terrible mistake. This should be r squared over 2. This becomes what? R squared over 2 over 2. Rho still cancels out. So this should be squared. Yeah. Okay, back at it. Good thing I caught that mistake. Otherwise, I had to record again. 2, and what height? This idea of a height is equal to that, right? So this is our second important equation. This height, we're gonna have some height, and we're gonna use that because, well, we have a large height, right? We're gonna use that to relate that. This is an expression which relates some height to omega. Okay, well, now what? Now we have I have a copying error. Yeah. Don't forget the G. Now what? You might be tempted to say, well, I have an expression for H now. If I know the initial height of my fluid, and now I know that there's some H added due to the angular acceleration, well, then I can just relate that to my angular acceleration and solve for that and say, boom, I have my maximum angular velocity. But that's not true. And I drew this diagram somewhat to scale to help and try and avoid that pitfall. You'll notice that, well, we start at some level, and when we start spinning around, the volume has to be conserved, right? This idea of volume when it starts being flung around, the initial height changes. It goes down, and we call that the level of depression. So it's not quite as simple. I wish we'd been done here, but we gotta do some more finessing. So let's try. The next natural question is, can I mathematically model that? And the answer is, of course, yes, we can mathematically model that. So let's move on to my next diagram, and we're going to use the idea of a conservation of volume, right? A volume balance. Well, if we have some, am I recording? Yes, I am. Wonderful. Oops. And if we have an idea of if this is going to depress some, well, whatever that maximum level of depression is, from here to here, the volume of this chunk of liquid has to equal the volume being flung to the sides. So let's go off and use that idea. Well, let's start with the easy one first. The left-hand side is quite easy. It's just a normal everyday cylinder, right? And we'll call the radius of the container big R. So pi r squared times d. This is the height, but we call it the level of depression. The right-hand side is not so simple. Okay, the height actually changes. The height actually changes with r, right? So height is a function of r. So this is your classic differential calculus. We can model this volume by saying, well, if I cut this cylinder up into concentric smaller cylinders, like a big onion, then I can say that the area of that is equal to this differential radius, infinitesimally small radius, multiplied by its circumference. That's the area. So what? 2 pi r. Right? And if I multiply that whole thing by some height, because the height changes, well then, I'm good to go. And you might be tempted to just wiggle this off 0 to big R, the radius, right? But you would be wrong here, and you would fall into a pitfall. Why? And I hinted at it earlier. That is because h changes. It is not a constant. You cannot just pull it out and just wing jungle the integral easy peasy. H is a function, and we have that function right there. We derived it moments earlier, right? So if I plug that in, that becomes what? So pi r squared d is equal to, let's pull my constants out. 2 pi omega squared over 2g integral of, oh, don't forget h. Oh, no. I put myself into a trap. Multiplied by what? R times R is r cubed dr. This looks rather nice and convenient, and it's my favorite thing in the world because things cancel out. Okay, so now I'm left with what? By the way, again, we're integrating from the center all the way to the center all the way to, the center all the way to the edge. So from 0 to big R being the radius of the entire container. So I have r squared d is equal to omega squared over g multiplied by r to the fourth, big R to the fourth, over 4. Over 4, right? Now what? If I bring big R to the other side, then I say that I keep saying angle. That's a very common saying, and my pattern recognizing brain is tempted to say angle of depression, but this is not an angle. This is level of depression. I say that my level of depression is equal to omega squared times r squared over 4g, and that is what? That is going to be my expression for level of depression. Okay. Well, now what? I have two expressions, an idea of a function of level of depression dependent on angular velocity and a height dependent on angular velocity. Let's see if we can relate this to the height of the beaker. So if I call the overall height of my beaker big H, and if I call the initial height of my fluid H naught, well then I can call this height right here. Call this height right here what? H naught minus D, right? H naught minus D. That makes geometric sense. Well, therefore, I can call my big H. H naught minus D plus H, right? Because I have H, this idea of an H, which is a function of the height of the fluid above the level of depression, dependent on radius and angular velocity. Well, let's plug and chug. This seems the end is in sight, right? So let's say that H is equal to H naught, and this is a provided problem statement, minus the level of depression, which is omega squared r squared over 4g, plus the function of height dependent on angular velocity. This looks rather convenient, right? I don't know why I wrote 2 G's. GG no re. Yeah. Am I done here? Yeah, I am. So now what? This looks two similar fractions. We can combine that. 1/2 minus 1/4 is what? 1/2 minus 1/4 is 1/4. So omega squared r squared. Oh, excuse me. Over 4g. Right? Now what? Again, let's remind ourselves of the answer, the question we're trying to answer, and it's because how fast can I spin my beaker without flinging everything out the edge, right? So what does that mean? The answer I'm looking for is how fast can I spin my beaker, right? So let's why don't we just go ahead and solve for that? So H, just basic algebra, right? This is not even the hardest algebra we've seen in this class. I just realized I made a sign error. Yes, I made a sign error. This should be that, because yes, 1/2 minus 1/4 is positive 1/4. Yes. So hopefully nobody caught that before I caught that. Otherwise, this wouldn't work, right? But let's move on. Now what? We're trying to isolate omega, right? So H, big H minus H naught multiplied by 4g over omega. Man, excuse me. Omega squared. Oh my gosh. R squared equals omega, all taking the square root of. We can simplify this a little, make this a little cleaner of an expression. GH minus H naught. Oops, what does that do? Over R, and there we go. Let's highlight that green. Green is good. Now we have our expression for it. If I have some beaker of a certain height, and I have some liquid filled up to initial height, and this beaker has a certain radius, well, if I plug all that in, then this will be how fast I can spin my beaker with the contents of the beaker just coming up to the edge but not quite coming over. Okay, so this will conclude homework 1 as a whole. Thanks.